Hey guys, so I'm gonna continue on what I said last time. Again, coin change problem again and again. This is what we left off last time. So I created a cleaner one. So it's a cleaner version of what I did last time. And what I want to talk about. So first off, if you haven't seen this graph, watch the previous video. Okay. Okay, so what am I trying to say here? Oh, yeah. So this is an example we went over last time, and the target in that case was 5. So the amount that we're trying to build was 5, okay? Okay, so maybe I can just stick it below here. The amount was 5, and these were the coins, okay? The coin values, okay? And okay, let me move this to the left. I think it's okay. Is that okay here? Yeah, I think it's fine. So last time we wrote the code that calculates the minimum number of coins needed to build particular amount. But the problem is I had to run to the bathroom and pee, so I did not really finish running the code. So let me run the code that we had last time, and let me see. Oh yeah, that one. Okay, so if I run this, it's working so far so good. These are 3 cases. Now the problem is, what's the problem? If I modify this test case, imagine if instead of 11 I put 20. Okay. Oh, okay, I got the result still correct. The result will be, what's the result? It doesn't show me the result. 4. Okay, 4 coins. Now instead of 20, let me make it 50. Now it's much slower, which means our solution had a very slow runtime. Duh, obviously, because I had to run. Oh my god, it's taken forever. So from 20 to 50, okay? So it couldn't even handle 50. Okay, so let's investigate what was wrong with my previous solution. It was not wrong, it's just slow, which is, in some sense, not good. Okay, so what was wrong? What is the runtime? Let's look at the runtime. What is the runtime? Well, the problem is we are spawning a new function, a new child node at for every single coin at every single layer. Okay? So this was for the 1 cent, this was for the 2 cents, this was for the 3 cents. Okay? Yep. And again here, we spawned a new node or made a new function call, created a new stack frame in memory for every single coin. Okay, so for example here, I think that will be a negative number, -1, -2, -3. So if you're trying to check how many function calls we had to do, okay, in our previous solution, well, here you created the 3 function calls. And here you created 9 function calls, right? 3 function calls, and then 3 plus 3 plus 3. Okay, what about here? Here we got also, I think also I'm missing this one. 3 will be here. So it's a 3 times 3 times 3 will be 27. Okay, why 27? Because it is 3 for every of the previous 3s. So you have 3 plus 3 plus 3 plus 3 plus 3 plus 3 get 9 times 3, which is 27. It doesn't have to be exactly 27, but just imagine the worst case scenario. So here, obviously, because it's a negative number, we don't have to continue. But you could imagine if this, instead of 5, it was much bigger number. We're looking at the worst case scenario. The point is, what I'm trying to make is, our tree size is growing exponentially, whereas every time for every level, we are creating a new function call, a new frame in the stack for every function call, sorry, for every coin, and which makes our function calls increases by a factor of 3. So multiply here by 3, multiply here by 3. Why is that? Because I have 3 coins, okay? And for every new amount, I'm spawning 3 different functions because I have 3 different coins. Okay, so for example here, 1, 2, 3, 1, 2, 3. Maybe the negatives, I don't have to create new functions call for them, but they don't have to be negatives. They could have been a different number. Here it's negative because I'm using a small number, which is 5. So what I'm trying to say is the runtime for this solution is exponential. It's O of 3 power n. Okay. Okay, why the 3? Because the number we're always multiplying by, which is factor of 3, we're always multiplying by 3, which means the tree is growing exponentially. Okay, if you really wanna see the proof for that, maybe you can go through it. Shall we go over it now? Okay. The point is, if you're adding 3 plus 3 power 2, well, 3 plus 1, and the first one will be 3 plus 3 power 0. That's 3 power 0 equal to 1 plus 3 power 1, and this will be 3 power 2. Add in 3 power 3, and then 3 power 3, and so on. This is called a geometric series. Okay? And geometric series until the very last number will be whatever 3 power the last number. Okay? Okay, geometric series, and it will be 3 power 0. That will be the runtime. And if you add all of these together, you could use a formula, and that formula is the first term multiplied by 1 minus the factor that you multiply by every time, which is 3, power the number of terms divided by 1 minus the number you multiply by. This is the formula to get the sum of a geometric series, okay? If you watched my video about climbing stairs, that should ring lots of bells. But this is called a geometric series. And its summation has a formula, and the formula is the one I wrote on the bottom. I think I need to move this a little bit. Okay, it's called geometric series. Serious? Are you serious? Okay. Number of terms. Okay, so A here represents the first term, so I'm gonna just put 1. That's the first term. And if you get the summation, it will be, well, you have negative, well, you can factor out the negative 2 on the bottom. So you could multiply by -1. So anyways, if you did the middle school math, that will give you 1/2 multiplied by 3 power number of terms minus 1. Okay, that will be the summation. Okay, which means for if you look at the number of terms, that's directly proportional to the value or the amount that we're trying to get to. Okay, so the number of terms I'm adding over here, how many terms are these? Well, it depends. Well, I'm going from 5 to 4 to 3 to 2 to 1 to 0, for example. So I have 5 different terms, okay? Because I have 5 different layers, 5 different levels, okay? So this, in that case, will be 1/2 times 3 power 5 minus 1. But if this was 100, that would have been 100, okay? And also depends on what coin dominations we're using, but the point is this is like the number of terms is directly proportional to the value or the amount that we're building. In that case, it's 5, it'll be 3 power 5. Okay, what if this was 100? If the 5 was 100, well, that could have been 100, 3 power 100. So if you notice, the number of function calls we're making is increasing exponentially. Okay, so this is the number of function calls we're making. Okay, so if the amount, this is the amount, and this is a number of calls, function calls. Okay, that's why I said in the beginning the runtime is O of 3 power n, but it doesn't have to be 3, right? Where did the 3 come from? Well, the 3 came because I have 3 different coins to use. If it was 5 different coins, there will be 5 power n. Okay, so if I were to go back, then the runtime is actually O of number of coins power n. So depending how many coins I have, 4 coins 4 power n, 5 coins 5 power n, and so on. So it's pretty slow. It's a very, very slow runtime. Okay? Okay. What can we do? What can we do? So if we look at our tree once more, we will note. I need to erase all of this. Sorry, I have to erase it to get some space. Kind of like gives me anxiety when I have so much clutter everywhere. Okay, so what can we do? What can we do is we need to optimize and see, did we do any redundant work? Did we repeat any work that we didn't have to repeat? If you look at this, for example, you will see, oh, no. You will see that this subtree is exactly the same as this one, is exactly the same as whatever subtree I could have gotten from here, but the definition could have space, which is this subtree. Okay, because it was using 2. Subtree is the same. And if you look at 3, well, actually, the subtree, believe it or not, is the same as the subtree. Woo, all of this. Ah. Okay. So there's so much work that's getting repeated. Lots of work that's getting repeated. Okay. I'm repeating the work how many times? For 3, I'm doing it twice. For 2, I'm doing it like 3 or 4 times. So we're repeating so much. We're making so many unnecessary function calls. So instead of repeating all that work so many times over and over, which is causing my solution to be very slow, what I can do, whatever answer I get from here, from this subtree, whatever answer this top guy over here is going to give me, whatever answer, in that case, it will be 1, because 2 is 1 level away from 0. I can just store it in some cache. Okay, let's store it here in some cache. I can create a cache, and I could say cache. We could say okay. Well, the answer for 2 that I got was 1, so store it there. Okay. And the answer, for example, for 3, let's look at maybe this 3 over here. Whenever the 3 finishes the answer, for example, it's going to be for this 3 is going to return 1 as well, because 3 is 1 level away from 0. Okay, because it's right beneath it. The 3 is going to, so I'm going to store the answer here. Okay. So every time I get the answer for some new unique value, then I store it somewhere in cache. Okay, so let's imagine now about to start a new function call over here. But do I really have to start a new one? Well, I don't really have to. Why is that? Because before I create all that mess over here, before I even think about creating all that mess, I can just look at my table first. And I see that I have the answer for 2 already. Okay? So all of this is not even needed. I wouldn't even have to create it or even go through it because I got it from the branch from a subtree on the right side. Okay? So that is going to save me all that work. Ooh, is saved. I don't have to go through it. Okay? Same for that guy over here. I don't have to do it again because I did it on the right, all the way on the right. Okay? Oh, actually, now if you think about it, now if you look at this guy over here, I don't even have to go through it at all because I have the answer from the left side. Okay, so I don't even have to go through any of that. Why? Because I went over it once all the way on the left side. Okay, so, okay, what do I mean? So what happens here? Well, in that case, what I'm gonna have is I'm gonna have a cache. It stores the unique values, the result for the unique values. So for example, for 2, for 3, for 4, for 1, and for 0. Okay. Okay. And then that's about it. So I'm gonna have the answer for every single unique value. Okay, so for example, over here, actually, this wouldn't be even needed. All of this too, I don't even need it because I did it all the way on the right side. Okay. And this is not even needed. Okay. Because I did the 2 before. Same thing for 1. Okay. Any branch was 1, any branch was 0. I don't even need it. Okay, so what does that mean? It means my runtime is going to be directly proportional to the 1. Let's see how many have 1 here, and then this 1 here. Okay, and I need to create 1 for this guy. So it's going to be about 5, 6, 7 different function calls. Okay. Okay, so instead of that many function calls over here, like way too many, all I had to do, I just had to cache my results. Which means whenever I make a function call with value 3, I'm like, oh, I have the answer. Sorry, here I have the answer. I got the answer from here. So I don't have to create the tree anymore. Okay. I make the function call, I see it 3, then I return the answer directly from the cache. Okay, so what's going to be the runtime? Okay, well, the runtime is I need to create my cache, obviously, to store the results. And at the very most, I need to create one function call for every single number. Okay, so I have a function call for 1, and I need only one function call for 0, one function call for 1, one function call for 2, one function call for 3, one function call for 4. Okay, maybe like 2 function calls for 3, 2 function calls for 2, but the point is this is not branching out. This will make the call and then go back directly. Okay. Okay, so the runtime, if I use the cache and try to convince yourself of that, it's going to be O of the amount. Okay, O of the amount. Or in that case, if you call the amount n, it will be O of n. Okay. I will need about, like, for amount of 5, for example, I need about 5, 7 function calls. So, okay, let's see. That's the whole idea. This is called memoization. I don't know why it's called that way. I thought it would have been called memorization, but called memoization. Okay. Memoization means you save the answer for problems you did before. Okay. Basically, you don't repeat the same problem over and over. You just save it. Okay. Okay, I hope that's clear, but let's write code for it.